good? Okay. All right.
Sorry, Mother, one more question. Has
Yeah.
anybody not checked out of the door? Let's say you checked out of the door. All right, awesome.
Okay. All right. So good morning, everyone. Today we're going to be talking about light curve analysis. And as Monsi said, I'm Melissa Hayes-Gehrke from University of Maryland. And I want to tell you right up front that I apologize if I leak out a few yawns. Just 3 days ago I was in Italy, and yesterday I was in Maryland, and today I'm here. And the time zones are really catching up with me. So, I apologize for that. But, light curves are so exciting, they're going to get me going here. So this is good. Now, I want to just mention, if you haven't gotten on it, nearpod.com. Okay, go to nearpod.com. You need a code. You don't need to log in. You just need the code in the top middle, FQXHK. And then that'll give you access to the slide. The reason we're doing this today, this is something that I use in my classes at the University of Maryland, is as we go through, we're going to have some additional tools rather than just slides as we go through. So if you're just watching on the screen, you won't be able to participate on those things. Okay, is everybody logged into Nearpod okay? Or did you get the code in? Okay, all right. So we're going to get started here. All right. So first thing to talk about is learning goals for this module. So our light curve analysis learning goals. Hopefully by the end of the module, you're going to be able to do these 4 things. So construct a scientifically plausible phase diagram from a raw light curve containing many epochs. Okay, so many sets of observations. And identify the type of variable represented in a light curve based on characteristics of a light curve, such as shape, period, and amplitude. And so that's something we're going to be talking about in just a moment, is not just how you analyze light curves, but why you do it and what kind of objects you may be looking at. And then discuss physical characteristics of the source based on characteristics of the light curve, and use different methods such as string length, Fourier analysis, and or Lomskargel periodogram methods to determine scientifically plausible periods from the raw light curves. Okay? And so we'll be going through and talking about some of these things. So let's start at the beginning here. Okay. So a light curve, and I am abbreviating light curve because we say it so many times in this module. Okay, so light curve is a series of measurements of brightness over time. And you can see that here. We often have it with Julian date or some form of Julian date, apparent magnitude, and you can see the brightness varying over time. Okay. All right. So when we analyze light curves, we're looking for things like characteristic light curve shapes and periodicities. And so I have a whole bunch of light curves on here. Don't worry if you can't read the axes very well. But the idea here is that you can see that a lot of objects have similar shapes to their light curves. And then other types of objects have different kinds of shapes to their light curves. And you can see that they repeat periodically. So they happen with the same light curve shape over and over. So these are 2 key things that we look for when we're analyzing light curves, are these characteristic shapes and periodicity. Okay. So now, this is something that you're going to be able to take advantage of with Nearpod here. So on Nearpod, you will be able to click through each of these sets of slides. And so when you're looking through each of these slides, I want you to see if you can kind of answer these questions to yourself. How do light curve shapes compare across different types? How does amplitude of variability compare across different types? How do periods compare across different types? So what I'm going to do is I'm going to give you like 5 to 7 minutes here to look through these slides on your own, kind of ask these questions, compare these different things on your own, and then I'm going to ask you some questions about it. And I should say, feel free to discuss this also with your neighbors. One thing I just found was very funny. These chairs move all over the place, and yet you guys all came in and lined them up in a row. You don't have to do that. If you can't see very well, move. If you want to talk to somebody, move. Please discuss this as you go along. So I'm going to give you 5 to 7 minutes to do this, and then I'm going to ask you a few questions. Okay, so go ahead. So you've got to click through the slides. I'm not doing this up here. You have to click through it on Nearpod. If anybody has questions on Nearpod about how to do this, let me know.
Help getting it to Nearpod.
Yeah, so did you go to nearpod.com? You want to put the code. Oh, you don't have a code button. There's usually a thing. Can you reload it? That is very strange. Can you scroll down a little bit?
Down?
Oh, here it is, right here. That's where you put it in. It just didn't load up for some reason. This code, FQXHK, yeah, there you go. Anybody else not on Nearpod yet? Okay, all right. Okay. You guys all able to scroll through?
Yeah.
Yeah, okay. Oh, you have constellations on your backpack. That is cool. You guys all scrolling through okay? Yeah. I'm going to give you about 2 more minutes to finish looking through these. Okay, so hopefully you've had a chance to kind of skim through these different types of variables and take a look at their different types of light curves. Now, probably most of you are not variable star experts. Did you realize there were so many different types of variable stars out there? There's a lot of different things, and this is not even comprehensive. So this is kind of some of the major types. want to ask you guys now a question about these. So here's a question for you. This is a polling question that you can do on Nearpod. And so please read the question, choose your answer, and I'll give you a few moments to answer. Okay, so let's get a few more answers here. This is not a hard question, so ready, 3, 2, 1, and we will share our results on this. And it should come in. There we go. Okay, so yeah, most of you said no. You can see, and some of you did just wake up, yes. Okay. And so you can see that the variable stars have really distinct light curve shapes, and that's one of the nice things about them is we can try to recognize them that way. Let me follow up with another question here. You should be able to read it on Nearpod. You're not on Nearpod, yeah. Yeah. Good question.
Work in the background.
Oh, okay. All right, so let's get a few more answers here. Okay. And 3, 2, 1, and we'll share. Okay. All right, so no. Yeah, you guys definitely notice there's a huge range in variability. Did anybody happen to notice some of the things, or one of the types of variable stars I mentioned that have like the shortest periods of variability? One of the shortest. Anybody catch that? Probably you didn't think about it specifically, and that's okay. Yeah. Delta Scuti? They can be short, but not probably the shortest that I had listed. Which one? Cepheids? Oh, no. No. Asteroids? Asteroids, maybe. Eclipsing binaries, yeah. Eclipsing binaries can be like 2 hours, 1 hour, less. Yeah, those can be very, very short. So eclipsing binaries are the ones I put were the shortest. Longest? Cepheids? Close. RR Lyrae? No, they're shorter than Cepheids.
I would say also eclipsing binaries.
Often, they could. Okay, so in principle, eclipsing binaries could have very long orbital periods. There's a selection bias there, right? What's the selection bias towards eclipsing binaries being short period? Yeah, the angle and what else? So both the angle of inclination, so that has to eclipse, and what else? I'm sorry? It's easier to find short period ones because you have to watch for a really long time. It's the same thing as a transit, like a planet transit, yeah. Miras have the longest periods. There can be hundreds of days. Yeah, okay. All right, now follow this up with a quick question for you guys. And short phrase. Whoops, sorry, it didn't come up yet. Please, short phrase, just a few words. I don't want any war and peace in this, okay? So, yes, short phrase. Think of this kind of word association. What's the first reason you think of? Write it down quickly. Okay. All right, I'm going to give you another count of 3 to finish your short phrase, and then we're going to look at a couple. So 3, 2, 1, And so let's look at a few answers. Your name will not be on it, so don't worry. Okay, share. How about this? Periods related to the underlying mechanism of the variability. Yeah, so it can tell us about something that's going on. Let's take a look at another one. Okay. Did I hit share? No, I didn't, sorry. Okay. Okay, so we got another one there, and let's do one more. Let's see. Okay, so yeah, so you guys got some good ideas here. So this is kind of our motivation. Why do we want to understand variable stars? So now let's go on to analyzing them. Okay, so usually when astronomers are able to determine the period of variability, they also determine the shape of the light curve. Those usually go hand in hand, which is very convenient. And both the period and light curve shape are crucial to identifying the type of the object, as you guys were just saying. So it's useful to look at the light curve phased by the period of variability. And so what do we mean by phasing it? And you may have run into this, you may not. And so I'm going to have this here. And so what I've done is I've taken a raw light curve. So this is the light curve for an asteroid called 1906 Naif. And the raw light curve is in hours. Asteroids rotate relatively rapidly. And you can see the observations, or each of the data points, the brightness of the asteroid. But if you just look at the top one, it's hard to tell what the period is of the rotation of the asteroid. There's a bunch of gaps in there. Why are there gaps in the light curve, the raw light curve in the top? What's one reason there's gaps in the light curve? Yeah, daytime. What might be another reason? What observation?
Observation is not happening.
Observation is not happening, and so it might be we didn't have control of the telescope. There could be bad weather, so on. So yeah, so there's always gaps, and phasing it makes it easier to see what's going on. So when we phase it, we basically guess at the period. Okay, now maybe it's an educated guess. I'm going to get into that in just a moment. And then we chop up the raw light curve into lengths of that period. So I've got these little lines that may be a little hard to see. So each of these lines is the length of our test period, 11 hours. And then we take each of them and overlay them on top of each other. So that's how we phase it. And then this graph shows the phase plot. It's from 0 to 1, or they've made it a little longer, 1.2. 0 is the start of the period, 1 is the end of the period. So it's like 0 to 100% of the period length. So this whole length of time is 11 hours because that's the period of the asteroid. When we phase it like this, we can see that a lot of the gaps are removed. The points overlie each other, and if this is the correct period, we get a sensible light curve. Okay, so phasing this out is very useful in testing periods and trying to see what the light curve shape is. And so often the plots that you see for variable objects are phase plots. A lot of the plots that you guys looked at in those slides were phase plots. Okay. All right. So the phase light curve is calculated by computing the phase of the observation. And these slides are going to be available to you. I've exported them from Nearpod, and they're uploaded to wherever all the slides are being uploaded to. So you will be able to get these. For the moment, you don't need to write down the equation because it will be in the notebook that we're using. Okay, so I'll just talk about it briefly. So the phase, and then we have to start it out at a certain time period, and then we subtract off integer values of the period, because what we're trying to do is get the fractional part of the period. So how far through the period is it? And so this is how we work out the phase. Okay, and I'm going to have you guys try to experiment with this in just a moment. First, I just want to show you the value and the effectiveness of creating a phased light curve. The top one is an unphased raw light curve from a Cepheid variable, and then the bottom one shows it phased to the proper period. And so if you looked at that top one, you would say, oh my gosh, I don't even see anything there. And then once you phase it, you can see the light curve of the Cepheid. Okay, so this is a very, very powerful way to look at your data. Okay. So now I'm going to have you guys experiment with this. This website is just to a Excel doc. So go ahead, pull it up. You may have to save it to your machine and then say that, change it from read-only into editing, okay? So I'm going to pull that up here so that you can edit it. I think it pops up by default in read-only. Okay. All right. So once you have this, this Excel doc is just a quick and simple way to phase something. And this is a Cepheid variable. And all you have to do in the Excel document is change the period here in days. Put in a new number. So, you know, I can test this out and say 2 days. And hit return, and it will replot it. Oh, that phase light curve looks like crap. That's not it. Yeah. So go ahead, take just like 2 minutes. Test this out. See if you can find the correct period for this just by testing out test periods. I can hear all the returns being hit. Yeah. Everyone testing it out. Yeah. Eight. Okay, I'm not going to give you forever on this because it could take forever. Is this a very frustrating exercise? Yeah, you can see where you could test periods forever and never hit on the correct test period. So that's going to get into what we're going to lead into next. Did anybody get something that you think is good? Tell me. I'm sorry, say it louder. 10.15. Ooh, 10.15. That is very close, yes. Ooh. And in fact, it is 10.148. So very good, yeah. Yeah. So this is a Cepheid variable. It's Zeta Gemini. Okay, so yeah. If you hit on the right thing, it's like, bam, magic. But you could flail around here forever and never hit on this, especially if it's high precision. You know, so what would 10.15, 10.16 look like? Bad. I only by 100th. Yeah, it doesn't take a whole lot. So we need a better way to try to find test periods to phase it to, because we can't just flail here forever. Now you can, in fact, write a computer program to go through and step through and test like all these periods and phase it and everything. That's, you know, really kind of the brute force method. Okay, I'm going to get rid of this for now, and let's go back. All right. Okay. So, question for you. Okay. All right, we need a few more answers here. Okay. And we'll get ready here in 3, 2, 1. And I'm not going to share this because we're pretty split between the answers. So we get to do something I love to do with my students. So this is discuss. I'd like you to introduce yourself to your neighbor if you don't know your neighbor. Introduce yourself and say which thing you answered and discuss. See if you can come to a consensus of which one is correct. And then I'm going to ask you to revote. So what I'm going to do is I'm going to move back. I'm going to move forward to the question. So revote once you come to a consensus. Whoops. Get rid of that. Oh, that didn't take much.
You know what? Yeah. My thought was that if you have this really, really short observation,
I just think that
Over a longer period, the difference would have zero
Okay. All right, once you come to a consensus, don't forget to revote. Don't forget to revote. All right. Don't forget to revote. Please revote.
I like this answer.
Okay. All right, so revote in 3, 2, 1, and we will share. Did I hit share? Maybe I didn't, sorry. There we go. All right. Okay. All right, so excellent. The variable star was measured over a relatively long time period. Why is that the important thing here? Anybody want to try to explain it? Yeah, you want to try?
it might not matter if you took all of your data in the same night, but if you take your data over 100 days, if you're 0.01 days off each day, it would get farther and farther off.
Okay. All right, does that make sense? That little 0.01 shift added up over like 100 days shifts everything a lot. This is one of the huge powers of light curve analysis, and having a long time baseline for your light curve analysis is you can get extremely precise periods out of pretty crappy data, honestly. So you could do pretty well on that. All right, but you got to know if you can get that kind of precision, you've got to have a better way to figure out a starting point to test. Because if you're just shooting in the dark, that's going to be really hard to do. So let's get to our analysis techniques here. So period determination methods. So we're going to have several of these here. Again, don't worry too much about getting the equations down, because we'll have them in the Python notebook for the ones that we're going to be having you working with, and you'll be able to look at the slides later. So the first period determination method I want to talk about is called the string length minimization method. So in this method, one imagines joining each of the data points with a length of string. Okay, so what you do is you phase the light curve to a trial period, and then once it's phased to the trial period, you imagine connecting all your points with a string, and then you calculate the string length. So this is just the distance between each data point, so the length of the strings, if you connected them all literally with a string. And then the trial period that has the minimum string length is likely to be the true period, because that will essentially minimize the scatter in your data points, because your string will be shorter if everything kind of follows together in a smooth curve. If your data points are really mixed up and down all over the place, your string is going to be really long, and so that's not going to be the best. Okay, so this is still sort of a brute force method, because you're doing a whole bunch of trial periods. The advantage, you don't have to necessarily look at the phase light curve for each trial period. Because if you're doing this brute force method and you actually have to look at each trial period, the phase diagram, that's going to take you forever. If this, you can narrow it down to some quantity of best ones that then you can examine by eye. Okay, so this is a kind of a brute force method, but it can be very useful. Okay. All right, so next method I want to talk about is called the Fourier, or I call it Fourier analysis. So in this method, you use sets of sine curves. And so trial sets of sine curves are fitted to the data, and a potentially complex repeating light curve shape can be created by combining multiple sine waves. And so here I'm just showing that. This top diagram here, this top wave, was created by adding these 3 sets of sine waves together. So you can see how if you can add together different types of sine waves with different amplitudes, different frequencies, you can create pretty much arbitrarily shapes of your light curves. Now this is again another brute force method, and it would take a lot of computational power. But this is something that is done in some cases. There's a course that I teach which the students study asteroids and look for asteroid rotation periods, and the method that the program they use to find periods or possible periods is this method. Okay, and it works well for that, especially since asteroids can have a little bit odd shapes in their light curves. You can make odd shapes with this. And so this is another way that you can try to find the best fit for your data and the best repeating light curve. Okay. Now, when you're fitting this, you could fit it to all of the data, or you could phase it to trial periods. It probably would be best to phase it to trial periods to do this and try to fit it, because you don't want to fit gaps in your data. Okay. All right. Now, I wanted to give you a chance to experiment a little bit with the idea of this Fourier analysis. So I have this tool. I tried to test it out on a bunch of different operating systems to make sure it would work for you guys. But what you can do with this tool is you can put in multiple sine curves. So the cycles 1, 0, 0, these are different sine curves. So if I change the 0, I've got different kinds of curves. And if I change this, whoops, to like a 3, then I change my curve again. So this gives you the opportunity to experiment with adding different kinds of sine curves together and seeing what you get. On the right side, it shows the total in blue and the separate light curves or the separate sine waves in green. So you can see how they work together. So if you just want to see the total, you could uncheck the parts and you can see, oh, that's the curve that I made from these parts. Okay. Go ahead and play with this just for a minute to get the idea of putting different sine curves together to make different shapes. I don't have a specific goal for this other than play with it, which I'm sure you'll be happy to do. Yeah. Is it working for everybody? Is it not working for anybody? Oh, yes. All right. You can add a curve as well. Okay. All right. Now I know we could play with this all day, but we're going to have to move on. So just to give you a little bit of a feel for that. Okay. We're going to move on to our next predetermination method. Oops. There we go. All right. Now, oh, sorry, we're not moving on. I just forgot to give you the equation for this. So for doing the Fourier fitting, so putting together the different sine waves, it becomes very complicated because you can add in arbitrary amounts of sine waves, so an arbitrary number. So you would have this kind of summation function. You have a mean magnitude of your light curve. You'd have some Fourier coefficients, a trial period time, and a 0-point time, and then the number of orders. So this is how many different sine curves you're adding in. Okay, so you just keep adding orders if you want to. The thing you have to be careful about with this is you can kind of overfit your data, because all of your data is probably going to have some kind of scatter to it, because we're not going to get perfect observations, and you don't want to be fitting the scatter. You want to be fitting what's really going on. All right, so for each trial, the function is fitted with linear least squares to light curve data. A range of trial periods and orders are fitted. Okay. Okay, so now the last method, oh no, I forgot. I'm going to actually skip this because I want to move on to the last method I keep talking about. Okay. Another method that we can do is to search for periodic signals in the light curve by computing something like the Fourier power spectrum from the light curve. So a formal Fourier transform of the light curve breaks down the light curve in each of its contributing sine wave frequencies. And it computes the power spectrum of the light curve, how much power exists in the light curve at each frequency. So I like this diagram kind of representing what's going on with the Fourier transform. So if you've got this weird light curve that's in red, and you see it's got this odd shape, you can kind of look at it by eye and say, oh, well, there's this little, there's these kind of bigger peaks that are sort of repeating, and I see some smaller peaks. Maybe they're repeating. So it looks like there's kind of several periods in there, but I'm not sure. How am I going to break that down? And so the Fourier transform basically breaks it down into, oh, there's sort of like 3 sine waves in here. And so it breaks down that there's some power at this frequency, at this frequency, and at this frequency, and it gives you this power spectrum. So you'll get a spike at each of the frequencies that are included there. Okay? So that's kind of the idea of what happens. And so let's talk about this. The more of a contribution, a sine wave of a particular frequency makes the larger the power that is computed by the Fourier spectrum, or the Fourier transform. And so I have a couple different examples of waves and then the Fourier transform and the power spectrum of those. So you can see a simple sine curve has most power, well, right at that frequency. So that's kind of the easy case. Here's a shorter one, so it's got less power, lower amplitude. And then here we see a more complicated curve. It has power at 3 different frequencies, and then another complicated curve, 2 different frequencies. So just giving you the idea of some example waves in the Fourier transforms. And then this is, so these on the left were no noise, but astronomers never get data with no noise. So with noise, over on the right, I have some examples. Random noise, the Fourier spectrum, or the power spectrum, basically shows no power at any particular frequency compared to the others. So they're all kind of even, so that is just noise. Here is a periodic signal with random noise. Now if you look at this, you can maybe sort of convince yourself there's an underlying signal in there, but it's hard to tell, is it noise or is there really something there? So the Fourier spectrum shows, oh yes, there's a lot of power at this frequency, and then the rest of it's kind of even, so that's the noise. And then here is a quasi-periodic signal with random noise. Now quasi-periodic means that it's not strictly periodic, but the period might change a little bit over time. So like an AGN might have a quasi-periodic signal. That's the best thing I can think of right now off the top of my head. And so in that case, you'll get a Fourier spectrum with the power being sort of at one frequency, but maybe a little bit of a range of frequencies. Okay, so this is one of the methods that you guys are going to be playing with in just a moment in your notebook. And so let me go on and talk about it a little bit more. Now, a true classic Fourier transform analysis requires the data points to be evenly spaced in time. And that never happens in astronomy. So we can't take that. So this type of Fourier spectrum or Fourier transform we're going to be using is called the Loam-Scargill periodogram, and it was developed for unevenly spaced data. Okay, so it's kind of adapted from the classic Fourier transform. And due to the formulation and approximations in the algorithm, it calculates an estimate of the Fourier power. It's not exactly the same quantity as a Fourier transform, but we still tend to call it power. That's how we compare it, and it makes the same kind of graph, so that's what we look at. So functionally, the periodogram can be used in the same way to indicate the most powerful frequencies. Okay, so here's a sample of the process here. So we have an unphased light curve, and I'm sorry the axes are kind of small, but don't worry about them too much. An unphased light curve. We run this through the Loam-Scargill periodogram, and we get a power spectrum. And this periodogram has a number of powers in here, a number of frequencies that have a lot of power. But the one with the highest power is at 0.61 days. So we say, let's try phasing to that period. And when we do, we see that the light curve makes sense. Okay, so that's an RR Lyry, and it has a 0.61 day period. Okay. Now maybe, I'll talk about this in a minute, maybe you try this one, and you can tell it doesn't make sense because the light curve, when you phase it to that, doesn't make anything sensible. Why would there be power maybe at these other frequencies? That could be due to some kind of noise source that's relatively periodic. It could also be due to things like day-night cycles. You might get power because you always observe for 8 hours, and then the night ends, and you're off for whatever many hours, and you start again and you observe for 8 hours. That kind of windowing can sometimes cause power. I'm sorry, go ahead.
Is it also just caused by the shape of the signal itself?
It's possible, yes. And in fact, you could also get power in aliases. So the shape of the signal, like for example, if you do have more of a sine wave, this isn't so pretty of a sine wave, but if you do have one like a Cepheid that looks a little bit more like a sine wave, you could get power at half the frequency or half the period and twice the period, for example. And so the pseudo power spectrum may show power at other frequencies, so this is what we were just saying, due to noise, harmonics in the data, and windowing of the data. So this is showing a periodogram, and the red line is showing the highest power, and that's the one it's phased to. But you can see that there's powers at other frequencies, again, due to noise or aliases, or maybe like the day-night cycle. And I think I have one more slide, and then we're going to get started on the, okay, yeah. Now, the Loam-Scargill periodogram, this is really messy. So we are very happy that Python has it in a function. So we will not be constructing this, but this is kind of how it goes together. So if you want to look it up, you can look up the Loam-Scargill periodogram. It takes into account the magnitude of the individual data points, the time the data point was observed, and then we have, of course, lots of scientific waves up here to analyze the frequencies that are in here. And then test the results. So you don't want to have that be the case. So we'll be employing the Loam-Scargill function in Python here. So this is how it comes out. Okay, and all right. My last kind of comment about this is when you're searching for true periods to whatever you're looking at, you have to make sure that you're not looking at an alias of the true period. So an alias period is a false period that's usually related to the true period or the observation frequency. Common aliases are 1/2 or 2 times, or periods near 12 or 24 hours. And so, for example, I have 2 asteroid curves. I have access to a lot of asteroid light curves, so I use them a lot in examples. And so the left one is half the period of the right one. The right one is the correct period. The left one is an alias. Okay, and usually you can think about aliases by trying to see, well, what kind of shape should the light curve have? How scattered are the data points? The data points are more scattered here. They follow a shape more closely there, and so you have that human intervention. And that is if you're thinking that's a really funky asteroid, that definitely is. That's why I like to show the light curve for that. And last thing. Okay, so once the period determination has been made, one must always look at the phase light curve to ensure that it makes sense for the type of variable object. Okay, so you've got as many peaks and troughs as you expect. The shape makes sense compared to what you expect. You always have to take a look at that. You know, don't trust the computers on everything. We have to kind of intervene and make sure that that's correct. Okay. All right. So what we're going to do from here is we're going to switch over to the Python notebook. And you guys know where the Python notebook is, right? So pull up light curve analysis. Go ahead and get started. I have to do a switch over with my computer up here to put it up on the screen. And so go ahead and get started, and once we're partway through, I'm going to ask you guys a few questions, but you'll be working for like 15 minutes or so before we do that. Okay, so go ahead and pull up light curve analysis. If you want to work with a neighbor, please feel free to consult. Okay. All right.